Welcome back, everyone. So today's pre-seminar speaker will be Akhila, and she will be talking about a subject to be determined, I guess. Groupoids. Interesting. All right, take it away.
Thank you for the introduction, and thank you for not trying to pronounce my last name, and which is easy for all of us. And yeah, the plan is to define groupoids, and then I'll shortly explain what is an ethyl groupoid, and then we will look at the construction of C-star algebras of groupoids. So let's start by defining a groupoid. Groupoid G. It is a long definition, and I will write down the whole thing just so that everyone has seen it. Is a set together with a subset G named I've created better for the time. G to G and an inverse map histogram is from G to G such that is equals to B1 if beta comma is in G2. That's that grammar is in G2. Okay, so that's the definition. So now let's see what it means. So a groupoid is just a set, and from the name groupoid, it is something that is supposed to look like a group, or which is kind of similar to group. So we have a multiplication map, but now this multiplication in group multiplication is defined on all of the elements, but here it is not defined everywhere. Like you cannot just randomly pick two elements from G and then multiply, but there is a subset, and this is called the set of all composable pairs. And there are certain pairs that you can compose. And also there is an inverse map, just like in the group, and it satisfies these properties. And this essentially says that the inverse of the inverse is just gamma itself. And then if we have two composable pairs, which means we can multiply two of these, then it is also possible to multiply the three, and then it satisfies the associative law, as in the group case. And to understand this better, let us look at a picture, and there is also, we can also define a certain subset, which is just set of gamma, gamma, and such that. And this is called the unit space. So a groupoid is just going to be, I have the unit space, and now I just draw arrows between these. So this associativity essentially says that if alpha, beta, so alpha. So if I have an arrow beta and then I have an arrow alpha such that the source of beta coincides with the range of alpha, then it is possible to compose these things, just like we do in functions. And then I would have something like alpha beta. And then if there is a different gamma, which goes like this, then it is again possible to compose all three of them. And then in that case, it doesn't matter which one I do first. So that is just associativity. And now this means that in group, we have a single unit, but now we don't have a single unit, but we have something called a unit space. So what it just says is that every element from the unit space essentially acts like a unit. So if I have a gamma that goes like this, and gamma eta. Okay, I don't have space for my eta. So let's draw another gamma. So if I have an eta that goes to gamma, then I can take gamma. I can take gamma eta, which is going to be this guy, and then the inverse of this guy, and this is just going to be gamma, and then in the other way around. And now I'm already confused with the arrows, but yeah, you understand what I mean. Yeah. And we have, I already used the term, but for completeness, we can define the maps. We have maps R and S that goes from G to the unit space called the range and source respectively. And R of gamma is just gamma gamma inverse, and source of gamma is just gamma inverse gamma. So if we have an arrow like this, and then if I want to go to the source, then I would first go to gamma and then come back by gamma inverse, and just like that. Now we can look at a few examples. First one would be any group G. Here the unit space is just the identity, and then every pairs of elements are composable, and yeah, we can consider it as a groupoid. A non-trivial example would be, let X be a set, and let gamma be a group acting on X. Then we can consider G to be the Cartesian product of the group with the set X. And here the unit space is going to be the identity of the group times X. And we can define the range, and source map as range of G time G comma X is just G dot X, and the source of Gx is just X. So here it is the action of the element G on X. And now we need to define how we multiply two things. So we know that if we take two elements, Gy and Hx, if I need to compose these two, then I know that the source of Gy should be equal to the range of Hx, and the range of Hx is nothing but H dot X. So the pairs that I can compose will essentially be of the form G and H dot X, Hx. So, and this is just GHX, the pair GH and X. And the inverse is defined by GX inverse is just G inverse and G dot X. And now the conditions for the groupoids essentially follows from the corresponding properties of group action, and also this groupoid in fact has a name. This is called the transformation groupoid. So if anyone has any doubts at this point, then please. Okay, now let's make things a little bit more interesting and consider topological groupoids. So what it is exactly what one would guess. Now we need a topology on our groupoid such that all of the things that we mentioned are going to be such that all of the maps that we mentioned are continuous. So a topological groupoid is a groupoid G include LP compact topology such that the unit space is Hausdorff and all the operations and maps R and S are continuous. I,
It's not a definition.
yeah.
People study non-Hausdorff.
Yes, but then again, then the unit space is Hausdorff, right?
Yeah.
So the group, we don't assume that our groupoid is Hausdorff, but unit space should be Hausdorff.
Yeah, that's 2,000 at least on your units.
Unit space, yeah.
Honestly, but yes, like most papers. We can have this debate.
Then you have to write two. You are an expert. If you assume just the multiplication and inverse, you say like R and S.
S.
Yeah, right.
Because usually people write it by the.
Yeah. Okay, and now let's define what is entire groupoid is. A topological groupoid G is eternal if the range map R is a local homeomorphism. So if we have the additional property that our range map is a local homeomorphism, then we call such groupoids étale. And once the range map is a local homeomorphism, we would again have that the source map is also a local homeomorphism. So this is kind of the property that is analogous to being discrete in the case of groups. So in particular, if you look at this example of a transformation groupoid, then here this would be an étale groupoid if and only if the acting group gamma is discrete. Now we move on to constructing C-star algebras. Now I'd be assuming that the groupoids that I'm considering is going to be Hausdorff. So let G be a locally compact second countable Hausdorff groupoid. We can consider now this is a Hausdorff space, and now this is a special case. And if we have time, we will talk a little bit about the non-Hausdorff space, but for now it is Hausdorff. Now we can consider the complex vector space. Cc of G of continuous functions with compact support, continuous functions with compact support. Then this is actually a star algebra with the following structures. I can define the star of two elements f and g as f and g gamma is just f of beta equals to gamma, f of alpha g beta, and f star of gamma is just f of gamma inverse. So we have this complex vector space, and now I can define the multiplication as follows, and then I put a star structure, and with these structures, this CCFG becomes a star algebra. So we have a star algebra. Now we need a C-star algebra. So we can take representations of this star algebra. And what we notice is that if phi is any star representation CCG on H, where H is a Hilbert space. That is, we have the map I from CC of G to B of H. Then for all F in CC of G, there exists Kf, constant Kf greater than 0 such that norm of phi of F is less than or equals to Kf. Now, this is true for any star representation of the star algebra, and this is a constant which only depends on this function f and not on the representation. So, which means that the set phi of f, where phi is a representation of CC of G, this is uniformly bounded. So using this, I can define a norm on this CC of G as norm of F is just the supremum over all representations of phi of F. Now we have a norm, and this is in fact a C star seminorm on CC of G. So we have a C star seminorm, so we just complete our star algebra with this norm to obtain the C star algebra C star of G, which is called the full C star algebra of the groupoid G. The full C star algebra of G. So this is the full C star algebra of G. We are going to consider two C star algebras. One is the full and the other one is the reduced one. So this is the full C star algebra. You just take all the representations and then you show that this collection is uniformly bounded so that you can define a norm this way. And then from this you get a C star seminorm and then you complete it. So this is the universal C star algebra. Now we would like to introduce the other C star algebra, which is the reduced C star algebra. For that, we have a small notation for x in the unit space. I denote by g of x the set of all gamma in G such that source of gamma equals x. So I denote by G suffix x to be the all elements of the groupoid which starts at x, whose source is x. Now we can define, so whenever reduced, this is kind of a standard construction. We have a lot of constructions with groups and all other things that we have seen. There are usually two C star algebras. One is the reduced one and the other one is the full one. And full one is usually a universal C star algebra, and the reduced one comes from regular representations. So that is exactly the process that we are also going to consider. So we need for now in the group case, if this was just a group, then we would consider the left regular representation. But now what happens is that now we have each of these, this is more scattered. The group is somehow, in some sense, more scattered than the group. So we would have to consider several representations, and then we would just take the direct sum. So for each x in G naught, there is a star representation. B of L2 Gx such that Ix of delta is just summation of the range of gamma delta alpha gamma. So this operates as shift operators. This is just the delta function, and where delta gamma of gamma prime equals to 1 if gamma equals gamma prime and 0 otherwise. So we have this representation pi x, and we take any function f and then evaluate it. If we evaluate it at delta gamma, then this is just going to be, here this condition is because for this to make sense. So we take all the alpha that can be composed with this gamma, and then we just sum it over. So this is called the regular representation by x is the regular representation associated to x. Now we have this representation corresponding to each of the elements in the unit space. So we can take the direct sum of all the images and this is going to be contained in direct sum of P of L2 of Gx and the completion of this direct sum in this guy is called the reduced C-star algebra. And it is denoted by this. So now we have the two C-star algebras, full and reduced. Do I have any time left?
A little bit late.
We started.
A little bit late. Okay. Okay. Maybe I have 3 minutes and then I'll go 5 minutes over time. So I have 8 minutes. Yeah. Thank you. So now this was all for the host of groupoid, and now I quickly want to say something about the known host of space. Before that, let me just put a small definition. A subset B in G is said to be a bisection. And injective. So if we have a subset B of the groupoid such that the restriction of the range and source map to B are invertible, then it is called a bisection. Now the construction of the reduced C-star algebra and the full C-star algebra that we did here was for the host of case. And now we don't assume that anymore. Now let's just consider let G be locally compact groupoid. with the unit space G naught host of. Now we can carry out a similar construction, but what happens is that instead of taking, I can't find it anymore. Yeah, instead of taking here the complex vector space of the compactly supported functions in G, we take all the bisections. We take CC of U, which is just the collection of all F continuous, F from U to C, such that it is continuous and compact support. So, and where U is a bisection. So you take an open bisection, and then you just consider the continuous compactly supported functions in this space. And now you can extend it to G, all of G by 0. So, and then one can consider C of G to be the span of F in CC of U open bisection. So we consider all the open bisections, and now then consider all the functions in CC of U, and then you take the linear combination of this guy, and then we call it C of G. But now this notation is not very good because these functions need not to be continuous anymore. So it's a bit tricky, but I cannot put it to the, okay, now it's better. So CC?
You write a difference then.
Yeah.
So, but you consider always the top one, right?
Yes. Yes, this is all of this is for retired groupoids. Yes. Yes. In fact, yes, these bisections form a base for your groupoid. So yeah, that's why this all things make sense. Yes, this would, yeah. So this would make sense. So yeah. And now we have this. This is again going to be a star algebra, and you can carry out a similar construction and obtain C star of G and the reduced C star algebra of G. Now, where I'm going with this is that now the situation is a bit tricky in the sense that now we have functions that are not continuous, and then there would be some functions that we don't want, essentially. So, which I think our speaker would explain more about. So yeah, so there is another, so when we assume that our groupoid is not host of, there is a better C star algebra that one can consider than the reduced C star algebra. So, which we can define as, okay, we call F in G singular if support of F has empty interior. So you consider the reduced C star algebra, and then if I have a function such that it's support, so support of a function is just set of all x such that f of x is non-zero. And if this support has an empty interior, then we call such a function singular. And this, when our groupoid is non-host of, this is in fact, this forms a non-trivial ideal. So let J be the ideal of singular functions. Now we have an idea, so we can quotient it. So these are all the guys that we don't want. So these are the guys who cause problems in our C-star algebra. So we just quotient all of that out, and then we define the essential C-star algebra to be C-star reduced quotiented by J. So this is more or less a better C-star algebra to consider for many reasons. And that's all I wanted to talk about. So thank you.
Questions? Right.
Transformation groupoid that you have. Can you put a topology on that to make it étal? What is it?
You can put just locally compact. Yeah, I mean, you can just put a topology on this. You can consider a topological group and then take a locally compact space X. So, and then if you want it to be étal, then the acting group should be discrete. Yeah.
Only by taking non-discrete group still get étal.
It has to be discrete group.
So that's an infinite one.
Speak of it out, that's actually like this discrete version of per group.
Yeah, the topological group is a totally,
Question. What would be the sister algebra, the groupoid sister algebra of this groupoid? Those connection.
Yes, that is going to be the cross product of the continuous functions or vanishing into infinity with this group. So yeah, which I kind of omitted, which I should have talked about, but it is going to be the cross product of that. Yeah, it is. That's a good question. I think it is the full for the full guy, isn't it? I'm not sure. It's the reduced, yeah. It should be.
Oh, no, we want to use it, so I think.
Oh, I see. Well, fair enough, yeah.
Thank you. Maybe this is more directed towards Tristan, actually. So where you, in the construction of the reduced groupoid algebra, you take the direct sum over all points in the unit space, right? Which is potentially like an uncountable set. Can you do that without thinking about it, or do you potentially run into some set theoretic issues there?
Regular representation just happen on G without partitioning these subspaces. So this is closer to regular representation, but regular representation generally like an object acting on itself.
Right.
So you can take instead of taking this direct sum, right away right now. Because this is naturally L2 G. So you don't need to partition. So this subspaces, so this is not equal to the direct sum of all these guys. So you can look at this, and then your regular representation. The final for this function, like L2 functions on G, it's nothing but a conclusion. And if this looks better, I don't know what people do all this time.
Right. Right. Thank you.
And just this is kind of more natural. I mean, I thought G, and that gives you the representation.
But I wanted to sometimes also with like GNS, the GNS representation, for example, and then you take a direct sum over the whole state space. Like, can I just always take direct sums over any sort of set of any element? It just feels a bit weird.
But usually the direct sum will always have, like any element direct sum will always have countable support.
In this expression, we have L2 of G with G uncountable.
Yeah.
The same problem.
Any questions from online? Otherwise, I think we'll take a quick break and thank the speaker again.